In this installment, we'll take a look at equilibrium. And there are three different types of our thoughts we have of equilibrium: static equilibrium, translational equilibrium, and disequilibrium. The three states surrounding equilibrium. And as we begin this, we'll start with a review of Newton's laws of motion, which we've already seen aren't anything unique. They are just restatements and particular cases of the law of conservation of momentum. The first of these Newton's laws is that a body will keep it wants to keep its current velocity. And you are familiar with the textbook memorized definition that most people have. An object in motion tends to stay in motion. Oh, keep its current velocity. An object at rest tends to stay at rest. Oh, keep its current velocity. Unless acted upon by an outside force. Now, this last part is not necessary. If something tends to stay in motion or tends to stay at rest, well, that means it keeps its current velocity. That implies that something else is going on. Newton's second law begins, the purest statement of Newton's second law is F net equals ma, but really what it is about is momentum. A change in momentum is mass times a change in velocity. And the rate of change of momentum, delta P over delta T, is m delta V over delta T. And Newton defined unbalanced force as the rate of change of momentum. And F net means the unbalanced force. It also means the sum of the forces. So the unbalanced force brings about a change in momentum at a particular rate. Not just any old change in momentum, but a particular rate. And of course, because delta V over delta T is acceleration, it ends up being ma. But all of that comes about because of the law of conservation of momentum. So F net, we said also, is the sum of the forces, sigma F, this symbol meaning sum of. So we add up all the forces, and if it's zero, well, then there is no net force. And if the net force is zero, the change in momentum is zero. The change in velocity is zero. We can rearrange Newton's second law, F net equals ma, for the acceleration, and then we could view it as the ratio of the unbalanced force to the mass of the body. But short of it is, this is the definition. It also means the sum of the forces. And the third law of Newton's is very commonly, for every action, there's an equal and opposite reaction, which is very confusing to most people. More simply stated, for every force, there is an opposing force. For there to be an interaction, there must be two. So the pure statement of Newton's third law is for every action, there's an equal and opposite reaction. We could view that more simply as for every force, there's an opposing force. And what that means is that for there to be an interaction between things, there must always be at least two. In other words, it takes two to tango. And I want to specify, and this is something that confuses many, many people, students and teachers alike, about action-reaction pairs. Action-reaction pairs refer to the fundamental interaction that brings the bodies together. And so what we might mean is we have a table and we have a block on the table. Now, of course, this is situated on Earth. And some people might want to say that the action-reaction pair is the normal force and gravity pulling it downward, like that. That is not the action-reaction pair. The action-reaction pair can be better visualized as if you had the block right there. At that instant in time, there is a force of gravity downward acting on the block, and there is a force upward acting on the Earth. It is the mutual attraction between the block and the Earth that is pulling this together. This is the action-reaction pair that's setting about motion. It's not moving when it's sitting on the table because there is actually another pair of forces here, and it has to do with the electrons on the bottom of the block and the electrons on the top of the table repelling each other. So these two are equal and opposite, the electrostatic forces, repulsive forces between the electrons of the book and the table. That is is actually another action-reaction pair. But the fundamental action-reaction pair is the mutual attraction of gravity, the force of the Earth on the block and the force of the block on the Earth. That is the action-reaction pair. The reason they don't accelerate toward each other is that the block encounters the table, and now there's a set of forces between the block and the table where the electrons are repressing each other. So Newton's third law, for every action there's an equal and opposite reaction. It takes two to tango. You can't just have one by itself bringing about the motion. So let's now talk about what static equilibrium is. Static equilibrium has that root stat, which means stationary. Now, equilibrium, the word equilibrium means equal. It means balanced. So static equilibrium means the forces are balanced. So the sum of the forces, which equals ma, is 0. If the sum of the forces is 0, then the acceleration is 0. And this little symbol, if you're not familiar with it, this triangle dots, means therefore. So the thought process goes like this. The sum of the forces is ma. And if the sum of the forces is 0, then a must be 0. And so if the acceleration is 0, that means